All right, so welcome back after the coffee break. Our next speaker is Professor Eric Maloney from Colorado State University. Yes, Eric, please.
All right, thank you very much for the invitation. I'm really excited to be at this meeting. So I'm going to talk about ocean-atmosphere interactions and intraseasonal oscillations in my talk today. A lot of the work I'm going to present was done by others, but there are some results from my research group that I'll show, and so I thank the many collaborators that contributed to this work. I also want to give a special thanks to Charlotte DeMott, who's a research scientist working in my group who helped to inspire a lot of the organization of this presentation today. And I'll show you a review paper that she just published over the last year that contributed some of these results. I also want to point out that if you want to follow me, there's a new site called Blue Sky that a lot of the scientific community in the United States is actually using to do scientific communication. So you could actually find me there using this handle if you're interested. All right, so I'm not going to go through this. You've seen this slide maybe once, maybe twice before, this animation of the MJO, but I wanted to bring up a couple of things that struck a chord with me during Daeun Kim's talk, actually, that are somewhat unrelated to my ocean-atmosphere interaction course. One thing is the effect of the mean state on the MJO, and one of the issues that I've been thinking about a lot is how the MJO is going to change in a future warmer climate. And if you look at CMIP6 models, they produce an El Nino-like warming pattern in a future warmer climate. But there's actually sort of a grand challenge in the climate community at the moment in that the observed warming pattern that's occurred over the last several decades doesn't look like El Nino. It looks more La Nina-like. And so one of the challenges, I think, from a climate community is to try to understand the differences in the warming pattern relative to what models predict. And it has a lot of impacts on things like monsoons in the South Asia and also the North American monsoon, places like that. Another thing that struck a chord with me in Daeun's talk was he talked about coupling of the QBO to the MJO. And I think in general, climate models don't do troposphere stratosphere coupling very well. And I was at a NOAA meeting last week where I was talking to Yi Ming, who used to be at GFDL, and he had a conversation with Isaac Held and brought up the interesting possibility that the inability of models to properly simulate the effects of like the slowly recovering ozone hole over the southern hemisphere and the impacts on the tropical stratosphere as it impacts the troposphere might be one of the things that the models are doing wrong and getting the SST pattern right. So anyways, thought those were a couple of interesting things that popped up from Daeun's talk. All right, so back to the topic at hand. I'm going to talk about ocean-atmosphere coupling. So I'm going to look at the MJO a lot. I'm also going to think about the boreal summer intraseasonal oscillation quite a bit in the context of air-sea coupling. As you know, Gilles gave a talk on the monsoon intraseasonal oscillations earlier in the meeting. In addition to there being eastward propagation during boreal summer, there's also northward propagation over India that helps determine monsoon active and break periods. So we'll talk about air-sea interaction in this context as well. Another effect of the MJ or the BSISO MJO during boreal summer is that there's also an effect on the Western Hemisphere. So this is a composite life cycle of the BSISO, and these panels are like 10 days apart. And you could clearly see the northward propagation over the Indian Ocean that affects this locale. But another thing that I wanted to point out here is that the MJO has a forced circulation response. So for example, you could see right here that there's enhanced precipitation associated with the MJO of BSISO over the Western Pacific. And this is associated with a forced circulation response that extends all the way to the coast of the Americas. And there's actually a secondary center associated with the BSISO over the region south of Mexico and Central America that is something of interest that I'll also mention, a few times here today in this talk. And this is also associated, like the Indian Ocean, with the modulation of tropical cyclone activity over this region as well. Okay, so first of all, let me show a plot here of sea surface temperature anomalies associated with an MJO. And this paper here is actually really interesting. This is a paper with Simon de Zurka that I wrote. Simon's at Oregon State University. And this is a paper that actually resulted from the last meeting I attended here at ICTS. So there was a monsoon workshop. There was a workshop in February of 2019 on air-sea interactions in the Bay of Bengal. And based on discussions from this workshop, Simon and I came up with this idea to look at the impact of sea surface temperatures on the MJO and BSISO, in particular the importance of sea surface temperature anomalies for forcing convergence that helps to moisten during certain phases of the MJO or BSISO life cycle. And this is one of the figures that came out of that paper. And what you can see here are sea surface temperature anomalies occurring for each of the MJO phases defined based on the Wheeler and Hendon index. And phase 7 is shown here just because that's when positive sea surface temperature anomalies start in the Indian Ocean. And what you see is an increase in ocean temperatures. And so by phase 8 and 1, you get maximum positive SST anomalies over the Indian Ocean. And it's subsequent to that, during MJO phases 1, 2, and 3, where you see the maximum precipitation. And the green contours here, a little bit hard to see, but the green contours showing you positive precipitation anomalies over the Indian Ocean. And then there's a resulting cooling of SSTs in the Indian Ocean. And then you see this whole pattern shifting off towards the east with time. There's no negative precipitation anomalies on here. All we did was accentuate the positive ones. But this gives you a sense of what the sea surface temperature anomaly field looks like associated with MJO events. And if you look at the amplitude here in a composite life cycle at least, maybe you get up to like 0.5 degrees Celsius positive and negative anomalies associated with the MJO life cycle. So this plot has continents. It's very messy. There's small sample size, things like that. Charlotte has a very nice figure in her review article of what the sea surface temperature anomaly field actually looks like relative to MJO convection, kind of in the schematic sense. And so you see this big MJO convective complex here, and you see colors below in the upper ocean. And so what this indicates is that typically you'll see enhanced SST anomalies off to the east of MJO convection and negative SST anomalies produced by the convective region with associated winds that occur off to the west. And conceptually, this whole thing moves off towards the east with time. So we'll talk about why these SST anomalies exist during this talk. We'll also talk about, are they important for understanding MJO and BSISO dynamics? There's mixed views on that, as Daeun Kim pointed out in his talk. And then we'll also talk about some of the scale interactions that we see associated with the MJO, especially with the Indian Ocean dipole and also ENSO. Okay, so that's the MJO. You could look at a similar view of SST anomalies relative to the BSISO. So this is a really interesting early study in 2001 showing for one particular summer the trace of sea surface temperatures over the Bay of Bengal and Arabian Sea, I think it is. I can't tell exactly. My eyes are bad. I can't tell where those buoys are. For one particular summer, and you could clearly see 40 to 50 day oscillation in sea surface temperatures at these buoy sites as the BSISO passed over. One other really interesting thing that doesn't show up terribly well here, but I'll talk about later, is that if you look at these higher SST periods, You also see a really strong diurnal cycle of sea surface temperatures associated with diurnal warm layers in the upper ocean. So it's kind of a jaggedy looking, feature at the peaks here. And I'll talk about the processes associated with that and whether or not, that's something you have to resolve to get, the MJO right in models and things like that. But anyways, this is a really nice early study. Here's a later study by Roxy and Tanimoto that looked at a spatial map of what sea surface temperatures look like relative to the BSISO. And here's a active phase of the BSISO here, associated with these positive contours as positive convection. And what you can see here is just like for the MJO moving east, you tend to get an increase in sea surface temperatures to the north of the northward moving convection and a decrease to the south. So this kind of looks like the eastward propagating MJO, but it's associated with northward movement in this particular case. I think this is the pre-active phase as they defined in this paper before the onset of this active ISO event. And then, I mentioned that we were also looking at the Eastern Pacific, and so the Eastern Pacific is a really interesting place of, obviously the cold tongue with ENSO variability of tropical instability waves in the ocean that produce intraseasonal SST variations. You have a feature called the Costa Rica Dome associated with wind gaps here. But this plot here shows the overall sea surface temperature variance during boreal summer on 30 to 90 day timescales. And so you can see that there's several different interesting features associated with high variability on those timescales. And there used to be a buoy at 8 north, 95 west, and this is the trace for a 4-year period associated with that buoy, completely unfiltered. And what you could see here is, just like the Indian Ocean, very well-defined variability in SST that varies on 40 to 50-day timescales over this region. You can see this in most summers. And spectral analysis, shows a very prominent peak both in precipitation and SST in this region. In fact, the signal to noise ratio of this 40 to 50-day signal is higher than anywhere I've seen in the tropics over this region. So really, really interesting subseasonal variability. The other thing I'll note about this region is that, we've done some modeling experiments with, one of my students helped to lead, where we took a GCM and ran it freely, and then also did an experiment where we isolated the East Pacific from the West Pacific by putting a sponge layer that prevented this Kelvin wave signal remote response from impinging on the East Pacific. And you could actually get self-contained 40 to 50-day variability in this region in isolation from the MJO. It's phase locks to the MJO, but it seems to be able to self-sustain intraseasonal variability in this region in isolation. And much like, and I won't dwell on this too much, but much like the Indian monsoon region, there's also northward propagation of intraseasonal variability in this region as well. And won't talk too much more about that. Okay, so what causes the sea surface temperature variability that you see here associated with an MJO? And these are two plots from two of Charlotte Demotte's papers. This plot here shows, kind of a composite MJO surface heat budget, where it shows the various components of the budget, including surface shortwave, surface long wave, surface latent heat flux, surface sensible heat flux, and then the net here. And then each of these bars represents the left-hand bar, the mean conditions, MJO suppressed conditions in red, and MJO active regions in, on the far right in this particular plot in red. And the sign convention here is interesting. So actually the sign convention is positive going down. And so positive going down means that heat is going into the ocean. So that's what that means. So the two biggest terms, the first order and the surface energy budget associated with the MJO are shortwave radiation and anomalies in shortwave radiation produced by the MJO and latent heat flux anomalies. So basically during MJO suppressed conditions, when you have fewer clouds, there's more of a shortwave flux into the ocean surface that helps to warm the ocean surface. And so that's one thing that's going on. And then latent heat flux is also a big term as well. So during MJO suppressed conditions, you tend to get a suppression of wind speed, and that suppression of wind speed leads to decreased evaporation from the ocean surface, and that is an anomalous warming of the ocean surface. So both increased shortwave radiation into the ocean surface and decreased latent heat flux out of the ocean surface during MJO quiescent conditions lead to a warming of the upper ocean, during MJO suppressed phases. Then it's just the opposite during active phases. So during active phases, you have more cloudiness that reflects more sunlight back to space, and you get a reduction of solar input into the ocean surface during those periods. And then also during MJO enhanced periods, you get stronger winds, not only stronger winds associated with large scale anomalous westerlies that underlie MJO convection, but you also get more cold pools, more gustiness, things like that as well. So you get an enhanced flux of heat out of the ocean surface during MJO suppressed conditions. And that, to first order, leads to an increase in SSTs during suppressed phases and a decrease in SSTs during enhanced phases. There's more to it than this, as I'll show you, but if you had a slab ocean model with a slab ocean depth of 20 meters, you could do a reasonably good job just with the surface energy budget of simulating these SST variations associated with the MJO. And there's a lot on this plot, but this basically provides a few harder numbers to support this figure on the left-hand side here. This plot. Yeah, so there's a lot going on. It's a little bit confusing, so I won't talk about it too much more, but it basically says the same thing as this. All right, so I mentioned, if you had a 20-meter slab ocean or something like that, you could get a reasonable depiction of what the sea surface temperature anomalies with the MJO look like. But it's actually a little bit more complicated than that, and it relates to that buoy plot of the Indian Ocean BSISO SST modulation that I showed before, where when you had warm SST periods, you tended to have this spiky behavior with diurnal warm layers forming. So this is the basic process, and so let's imagine that we are in quiescent MJO conditions, relatively cloud-free, relatively wind-free. When you get these sorts of conditions, you could have the following process. So you get a really big shortwave flux during the day. So this is shortwave radiation on the top here. And because you have really low wind conditions, you can get the support of a really shallow diurnal mixed layer right near the ocean surface that might be only like a half meter to a meter deep. And this can form because there's not strong enough wind mixing to mix down this shallow diurnal warm layer down to depth. And if you have a really shallow diurnal warm layer like this, then it doesn't have that much heat capacity compared to like a 20-meter deep mixed layer. So you could heat it and cool it very, very rapidly. Clearly, there's other issues like shortwave radiation penetration through the base of it and stuff like that. But you can get, in general, very rapid SST warming during the afternoon, in this diurnal warm layer. So if you look at the SST, you kind of have this, background nighttime SST condition, but you could get formation of a really strong SST peak that, exists, just during the daytime. associated with this diurnal warm layer, and it might be an SST peak of like a degree or something, relative to the nighttime state. So this is a time series from Burney et al. 2007, showing a SST from a Toga Core buoy in the Western Tropical Pacific. And I can't remember when this is. This is a given year, but in black here, you could clearly see kind of the background SST condition, and in red here, you could see the presence of this diurnal peak that exists due to formation of diurnal warm layers. And the interesting thing again is that you tend to get the diurnal warm layers when you get this general warming of SSTs occurring, which occurs during the suppressed phase of the MJO, where there's very low wind conditions. You see this for many of these different events. And it's kind of hard to see on here, but there's two lines. There's this black line and this blue line. The blue line represents the effect of the diurnal warm layer warming on daily mean SST conditions. And I think the black line is what would happen if you didn't have this diurnal warming occurring. And so you see that there's maybe, I don't know, a 0.1 to 0.2 degrees Celsius effect of these diurnal warm layer processes on the daily mean SST. So if you don't have those, it could, for example, in your climate model, if you have coupling only once a day, decrease your intraseasonal SST anomalies. And again, this is kind of a schematic of the same thing. So this is the suppressed phase of the MJO, and you can imagine that this is daytime. During the suppressed phase of the MJO, you can get formation of these diurnal warm layers that cause a really thin warm layer of SST right near the ocean surface. During disturbed periods, the enhanced phase of the MJO looks very different. You get wind mixing that pretty much mixes everything down to 50 meters or so depth. So two different different conditions. There are things that affect diurnal warm layers, like rainfall on the ocean surface can cause a negative buoyancy flux onto the ocean surface associated with low salinity. And those can also foster diurnal warm layer formation. And then there's a lot of other, complicated things on here that I won't talk about, like barrier layers and things like that. But anyways, this is a nice schematic of the effect of calm conditions on creating diurnal warm layers. All right. So one question, I guess, and this is something Gayen covered very quickly, is whether or not ocean coupling is important to MJO dynamics. So that's a key question that I don't think we've completely answered yet in the MJO tropical meteorology community, but I'll talk about a few ideas on this. All right, so one thing does seem to be certainly true. So this is a paper that I wrote with Adam Sobel in 2004. And what this is a bunch of simulations with the NCAR community atmosphere model, where we have a slab ocean applied to the to the model, and we've varied the slab ocean depth. And actually, we've varied the slab ocean depth between infinity, so basically fixed SSTs, all the way to 2 meters or even lower. I think we went down to 1 meter in one case, so we didn't show it in here. So this is 50 meter slab ocean depth. This is 2 meter slab ocean depth. And you could see here, and there's no observations on here. This is just models, but you could see with the 50 meter slab ocean depth, there's eastward propagation of MJO convection over the Indian Ocean and Western Pacific. Doesn't look that different for 20 meter slab ocean depth, nor 10 for that matter. But once you start getting down to some of these shallower slab ocean depths, you start to shut off the MJO in these simulations. So basically what's happening in this simulation here is you are decreasing the ocean depth to such a shallow extent that you're essentially shutting off surface evaporative latent heat flux anomalies in the process of doing this. So what happens is that if you impose a wind speed anomaly on the ocean surface that wants to drive evaporation, because the ocean is so shallow, there is a very rapid cooling of the ocean, and it produces an air-sea humidity difference anomaly that actually counteracts the wind speed anomaly that's imposed on the ocean surface to drive the flux. So in effect, with these very shallow mixed layers, you are shutting off surface evaporation. And so we actually did another run, what we call a no-wishy run, where we shut off wind evaporation feedbacks, and it basically has the same effect as having a really, really shallow mixed layer. Anyway, so this is one side of the spectrum. So if you vary the MJO between a coupled simulation with realistic mixed layer depths and reduce the capacity of the mixed layer, you shut off the MJO. But when people think about air-sea coupling, what they're basically thinking about is going from an infinite depth mixed layer of infinite heat capacity to a slab ocean that's more like 20 meters, which is a characteristic slab ocean depth. I'm sorry, mixed layer depth of the tropical Pacific, for example. So that's what most of the coupling studies are trying to look at. Going from infinite heat capacity to one that's like 20 meters. Okay, and so certainly some studies have shown that ocean coupling does produce stronger MJO simulations. So here's another, Hofmiller type plot of observed MJO convection here, moving off towards the east. And this is a paper that I contributed to by Qidong Zhang in 2006, showing a series of 4 models. So there's an Australian model, GFS here. This is a model that I ran, a version of the NCAR community atmosphere model, and here's ECM. And each of these models has an uncoupled version with a fixed SST, essentially infinite depth, mixed layer, and then a coupled version of the model here. And I think we ran these with 50-meter depth mixed layers, if I'm not mistaken. But what you can see here is that at least in this series of models, consistently the active coupling actually strengthens the MJO. So it seems like there is some evidence that coupled simulations do produce better MJO simulations, at least for some models. And I'll talk about why that might be in a little bit. And then a similar thing has been demonstrated for the BSISO. So this is a paper by Joshua Fu and Bin Wang in 2004. And what they were looking at is boreal summer. And this is an uncoupled version of a model that they were using. And this is a very interesting wave number frequency spectrum in that northward propagation is shown on the right and southward propagation on the left. So it captures the BSISO propagation and not the eastward MJO propagation. But this is the uncoupled version, this is the coupled version, and this is the difference. And you can see that with ocean coupling, this BSISO has increased in strength. So that's some more evidence for why why ocean coupling might need to be included to get the right strength BSISO. Okay, so why might ocean coupling help to modulate the MJO? So I'm going to present a few different hypotheses. There are others in addition to the ones I present here, but I want to talk about some of the leading ones that people like Steve Woolnough and Charlotte DeMott have thought about in some detail. One possibility is that SST anomalies associated with the MJO enhance surface convergence in the boundary layer that acts as a moistening agent. So this was a hypothesis that was originally formulated by Lindzen and Negum in 1987 and has been carried forward since by others like Larissa Back and Chris Bretherton and Bjorn Stevens and others, in thinking about, what regulates convection in the tropics. And the basic idea, I'll walk through on here. And so this is a paper from one of my former students, Adam Ridback, and I'll show you how he applied this in a little bit. But this is a idealized simulation of the atmospheric flow in the lower atmosphere if you give an SST field that looks like this. So there's high SST in the middle. That's maybe a degree higher than that at the flanks, like 1,000 kilometers to either side. So there's higher SST here. And imagine that you have a boundary layer top that is roughly at the same pressure everywhere. So let's assume that the boundary layer top is the same everywhere. If you use hydrostatic balance and do a downward integration of a warm boundary layer relative to a colder boundary layer, what you're going to find is that if you start from the same value at boundary layer top, you're going to end up with a low surface pressure over the highest SSTs and warmest atmospheric boundary layer. So there's a low pressure that basically forms over this high SST region right in the middle of this plot with higher pressure on either sides. And the response of this low pressure that you see in the middle of this scene is to drive low-level boundary layer convergence towards the highest SST, and then there's an upward, a vertical velocity, near the boundary layer top. And so basically, what this convergence in the boundary layer forced by this SST field is going to produce is this going to produce moisture convergence and moistening. So if you have an MJO moisture anomaly with sufficiently strong SST gradients near the equator, that's going to be able to drive surface convergence and act as a moistening process that can be diagnosed using the moist static energy budget relative to other terms. So that's the basic idea here. This plot also shows rainfall produced in this model too. I won't talk about that right now. Okay, so Simon DeZerka and I used a mixed layer model of Back and Bretherton 2009 to actually diagnose how big the effect of this moisture convergence is if you produce an MJO SST anomaly that looks like this. So this is the SST anomaly I showed before, and this field here is the moisture convergence anomaly field that's generated in response to these SST anomalies. And where you see red here, that's surface convergence occurring as a result of this SST field and convergence into that positive SST maximum. So we computed this boundary layer moisture convergence, and we computed the rest of the terms in the vertically integrated moist static energy budget as a comparison to how large this was. And it's conceivable that this boundary layer moisture convergence driven by these SST anomalies is of the same order of magnitude as the other terms in the moist static energy tendency budget. So this term is potentially one of the key drivers for the MJO moisture tendency that not only can explain the buildup of moisture in the Indian Ocean, but also can explain the eastward propagation of the MJO off to the east of MJO convection. This has also been thought about by other people. We weren't the first to think about it. Andrew Marshall, Harry Hendon, and others have thought about the impact of increased convergence produced by SST anomalies in their model. So it's conceivable that this is a very important process for explaining the tendency of the MJO moisture field. There's a lot of free parameters in this model, so depending on how you that are not very well constrained. So depending on what parameters you use, you could get much higher or much lower. So there's still a lot of work that needs to be done to think about this. All right, so driving convergence is one possibility. Another possibility is the impact of these SST anomalies on surface fluxes. So this is an analysis done by DeMott et al. 2016. And what they did was they partitioned the formula, linearized the formula for latent heat fluxes into three different parts. And two of the key parts here were associated, one of the key parts here was associated with anomalous air-sea humidity differences acting on the mean velocity field. And then there's another term here, which I'm not showing, is the wind-driven part, which is the MJO wind anomalies acting on the mean air-sea humidity difference field. This is the one I'll concentrate on here. I also have the sensible heat flux part here too. But if you have an MJO SST anomaly that's formed, and you make assumptions about the relative humidity of the boundary layer being relatively invariant and things like that, you could produce an anomalous air-sea humidity difference associated with that MJO SST anomaly. And this particular figure here shows the effect of those SST anomalies on surface fluxes. This is done on a location by location basis, so there's no propagation in this plot. So time zero, lag zero here basically represents lag zero at every single location. And what you can see here is that there are red colors here associated with this term basically that indicates that the presence of MJO SST anomalies produces a very slight increase in surface flux out to the east of MJO convection. So that's basically, what this plot is showing. Really not big, maybe half a watt per meter squared, 1 watt per meter squared, something like that. But it's a non-negligible part of the moisture tendency budget that, might help to propagate the MJO eastward. So another factor that might help to, feed these SST anomalies back onto the moisture budget of the MJO. All right, there's another hypothesis that I won't talk about too much, but Dave Randall and Charlotte DeMott and others also looked at the impact of flux air-sea coupling on changing the spatial distribution of MJO convection. And they actually found with a version of the superparameterized community atmosphere model that an interactive ocean concentrated convection more onto the equator. And they argued that this concentration of MJO convection onto the equator produced a stronger dynamical response, shown here with the Rossby gyres and Kelvin wave response that led to better eastward propagation of the MJO. So another idea here. And I do think that this mechanism might actually relate to some of this discussion of the meridional moisture gradient as well that Dae-Un Kim talked about in the last paper. I'm not sure if they looked at the meridional moisture gradient in this paper, but I suspect it's stronger with a coupled model where you concentrate convection more on the equator. All right, so maybe there's some legitimate ideas for, more interesting ideas for how coupling improves the MJO. There are some other maybe less interesting ideas for how coupling, indirect ideas for how coupling might simulate the MJO. One is that the act of coupling can change the mean state of the model. And so there's a quote in here from Klingemann and DeMott talking about that fact. So simulated coupled model mean state biases affect the perceived response of the MJO to coupling. So their paper used a ocean mixed layer model called KPP, where they were able to constrain the sea surface temperatures, but still allow ocean coupling to occur. Through mixing processes and other processes. So they showed that if you impose in this one-dimensional coupled model the SST field from either uncoupled models or fully coupled models, then you could show that, you know, in many cases it was the mean state of the couple simulations that had as big or dominant reason for controlling the perceived impact of coupling in the models. I don't think that came out very well, but basically the mean state is a possibly an important indirect effect of coupling that can affect the MJO. And then Gilles Bellon also looked at this in the context of the BSISO. So basically, they said that ocean-atmosphere coupling is shown to have either little impact on the growth rate or latitude structure of the atmospheric oscillation, but maybe it affects the period. So again, it's not essential for the existence of the ISO in the model, but it does have some second-order effects by affecting maybe the strength of northward propagation, speed of northward propagation, and stuff like that. And then Xu Guang, who gave a talk last week, looked at a given BSISO during the summer of 2016. And they ran a version of WRF in coupled versus uncoupled form. And they basically came to the same conclusion that coupling had a very little impact on BSISO simulation. So anyways, I think it's still up in the air how coupling affects the MJO and BSISO, whether it's an active effective coupling on each MJO disturbance, through producing convergence or flux variations or something like that, or it's through the mean state where coupling is important. So I think there's still some work that needs to be done to understand that. When do we need to end here, by the way? 5? 10 minutes, okay. I think we're fine. All right, I also wanted to talk about some cross-scale interactions involving air-sea feedbacks between the MJO and other climate phenomena. One thing that I want to point out first before I dive into some of the discussion of the Indian Ocean dipole are some results from this paper by Rydbeck and Jensen. And this is a really interesting study that brings in ocean wave dynamics and thinking about MJO initiation in the Indian Ocean. So imagine here on this plot that you have an MJO event in the Eastern Indian Ocean, kind of like we have now, with strong westerly anomalies on the ocean surface. So the strong westerly anomalies on the ocean surface are actually going to force high sea level height in the Eastern Indian Ocean associated with a Kelvin wave response to that wind stress. And you can see that Kelvin wave impinging upon the coast of Sumatra here. There are wave reflection processes in the ocean such that when a Kelvin wave reaches an eastern boundary, there will be reflection of that wave back towards the west in the form of equatorial Rossby waves. So if you follow this along here, you could see, especially right here, these two sea surface height anomaly centers straddling the equator. What these are equatorial Rossby waves that were generated in response to Kelvin wave reflection off the east coast here, west coast here of Sumatra. And it basically takes, let's see here, this is day minus 60 and this is day 0, about 60 days for this reflected response to reach back into the Western Indian Ocean here. So one thing that this paper argues is that these sea surface height anomalies that are also associated with thermodecline depth anomalies, so deep thermocline, can lead to formation of warm ocean temperatures in this region that could help to initiate MJO events. So that's the argument in this paper. I'm not going to talk too much more about that. But one thing I will talk about is the potential role of this for initiating Indian Ocean dipole events. And so we maybe saw this in 2019. So the Indian Ocean dipole, many of you, likely know what this is. There's a positive phase and a negative phase. The positive phase is associated with enhanced convection and warm SSTs in the Western Indian Ocean, easterly anomalies. Negative phase, just the opposite, cold SSTs in the Western Indian Ocean, positive anomalies on the other side. This is an index of the IOD, and I wanted to motivate this by this spike right here. So this is one of the biggest Indian Ocean dipole events that occurred in the record, and it happened late in the year 2019. Basically the fall after I was here last in India. This is a really, really interesting event that actually had global consequences. So I was actually I was in a field program, another field program here in Costa Rica with Dave Raymond and a few others, a field program called OTREC. And early September, there wasn't really much going on. It was really boring along the coast. We were wanting to look at easterly waves and things like that, and there was not much happening. But then this huge Indian Ocean dipole event started to arise very rapidly in the Indian Ocean. Associated with a dipole of convection across the Indian Ocean. And one effect of it is actually shown in this plot here of sea level pressure anomalies for, I think this is even a given day in September, but a lot of late September kind of look like this. And what you can see is generation of this really notable sea level pressure trough across the entire Pacific that was generated as a forced response to convection anomalies over the Indian Ocean. And it hits the Andes. The Andes are really like a wall. So, kind of hits the Andes here. You sort of see it bleeding around the Andes. But this had the effect of reorganizing convection across the entire Eastern Pacific. And it actually, produce convection and low pressure along the coast, and relatively high pressure along the equator, and produce a complete regime change over the Indian Ocean associated with what was going on over here. So we thought a lot about this during the field program and found it fascinating that this huge event occurred that reorganized the entire tropics. And of course, a lot of people have looked at, the teleconnections associated with, with events like this. So I've contributed to a paper with Laurel de Serra at Columbia and Angel Munoz in Barcelona on the potential role of the MJO in forcing this 2019 IOD event. So this is one of these Wheeler and Hendon plots, showing magnitude of the MJO and its phase, and there were very strong MJO events occurring across the tropics in the spring and summer of 2019. This one here in April of 2019 was particularly strong in the Western Indian Ocean, but then there was another one in June right here as well. So these two events might have had something to do associated with the onset of this IOD event that we saw in the Indian Ocean. So I'll show you a few plots here of sea level height anomalies, sea surface height anomalies during 2019. This is January here, and it goes down to the end of December 2019 here. And these are height fields at two different latitudes. This is the equator. This is where you would expect, the MJO's impact on oceanic Kelvin waves to be strong. And this is 5 degrees south. This is one of the latitudes where oceanic Rossby waves would have strong sea surface height reflections. And I noted those two strong MJO events that occurred in April and June. And you could see them here in sea surface height anomalies. So you could see generation of eastward propagating sea surface height anomalies that hit the coast of Sumatra. So the coast of Sumatra is basically like right here. So one reaches here basically around the beginning of May. Another one reaches here sometime in late June. And what you could see in response to this, especially the first one, but there's also evidence you could convince yourself of the second one, of Rossby wave reflection. And there's very slow propagation, like 1 meter per second of these Rossby waves off towards the west. And the initiation of this strong Indian Ocean dipole event was somewhere around here. So it's approximately coincident with when you have this reflective wave signal reaching the Western Indian Ocean when you saw the big blow up of this particular event. So probably need to do some modeling studies to show this conclusively, but there's at least some circumstantial evidence from looking at observed sea surface height fields that the MJO had something to do with this production of the IOD. Okay, I probably don't have too much more time here. 5 minutes, all right. Unfortunately, my movie doesn't work. I was really wanting to show, maybe I'll have to send it to you afterwards. I was really wanting to show you this movie, but I was gonna show you evidence that the MJO also has important implications for El Nino Southern Oscillation as well. And what this video was gonna show you was the initiation of the 97-98 El Nino event that started with, I don't know why I'm walking up there. I do that during class. Started with this really strong westerly wind event at low levels associated with the MJO. And what you could see in March of 1997 is, through Ekman convergence, the buildup of sea surface height in the, Western equatorial Pacific, associated with this event. And what I was going to show you on here is an animation that goes through the end of 1997, showing really impressive evidence of an oceanic Kelvin wave, going all the way to the coast of the Americas and triggering the warm event that occurred later in that year. There's also evidence of Kelvin waves going up the coast all the way up to San Francisco Bay and stuff like that, if you follow that. And again, supposed to be an animation, but maybe I'll send it to you later. This is a still image of the same thing. So this is a paper by McFadden, 1999, showing the processes that led to this 97-98 El Nino event. And so I was talking about this wind stress feature out here in the Western Tropical Pacific. And so that was the starting point. And this is isotherm depth anomalies, which are, they correspond to sea level height anomalies. They're out of phase with one another. And what you could see here is the generation of this, approximately 2.5 meter per second signal in isotherm depth anomalies that propagates across the entire Pacific. And this is, associated with the generation of this warm event. And so you can see deeper thermocline SST anomalies occurring, across the entire Eastern Pacific after that occurred. One thing that there's a big body of literature looking at interactions between the MJO and El Nino, and one thing that's become a very hot topic is thinking about state-dependent noise and the mutual interaction of the El Nino and MJO events at the beginning of the initiation of strong ENSO, warm events. And you could kind of see that here. So you could kind of see here that these westerly wind bursts associated with the MJO are kind of marching off towards the east with time. And these kind of follow the eastward movement of the West Pacific warm pool as this warm event develops. So people like Fei Jin and others have thought a lot about this state dependency and how MJO activity changes as you change the state of El Nino. It doesn't seem like the MJO is doing its own thing randomly in independence from El Nino. There seems to be some mutual support for each other as this develops. This one? It's probably, yeah, I don't know. So one interesting thing that we're actually thinking about is that there's not always a strong mapping of westerly wind burst strength onto the strength of the Kelvin wave that's produced. And we're actually have a NOAA project to looking at that now and why that occurs. And so this wave is probably generated by this feature here, but it certainly doesn't look like a really strong event. And so there's other factors that seem to determine how strong an ocean Kelvin wave is in response to a wind forcing. So to study some of these processes, this is my last slide here. There's actually going to be a field experiment in the central and western tropical Pacific in 2026 and 2027 called TPEX, so the Tropical Pacific Ocean Observing System Equatorial Pacific Experiment. And one of the specific goals of this experiment is to understand how El Nino onset occurs and how the MJO contributes to El Nino onset. Obviously, if you're just going for a field experiment for 1 year, you're unlikely to get an El Nino initiation. I mean, you have a 1 out of 7 chance or something like that. But even in a random year, you will see eastward excursions of the Western Pacific warm pool that are forced by atmospheric wind stress and Kelvin waves. So even if there's no El Nino initiation, you will see variability in the warm pool edge that you'll learn something from. So anyways, they're going to go out there in 2016 and 26 and 27. There's going to be a sort of Central Pacific array right at the dateline, and then there's going to be another one more across the cold tongue here at 140 degrees west. And there's going to be, an array of buoys and aircraft and radar observations and things like that. So if you're interested, I'd be happy to send you a copy of the TPEX science plan. But it's basically to study some of these interactions, multi-scale interactions between the MJO and other disturbances. And then the last thing I'll put up here is that this is a great resource for more detail on some of these topics. This was actually just published this year. There's a volume on the Indian Ocean and its role in the global climate system, various chapters, and this chapter on intraseasonal variability in the Indian monsoon region is something I drew from a lot when I was developing this talk. So I'll leave it there. Thank you very much.
Yes, questions for Eric? Yes, take microphone.
Yeah, so overall, there is only, please first confirm whether I have understood correctly. So for the direct effect of SST in the moistening for these intraseasonal oscillations, the only 2 ways is either the Wishy way or the Lindsay-Digam or Back-Bretherton way, right?
I wouldn't say it's the only 2 ways. It's the only. I just highlighted a couple of ways. There could be others.
Yeah, I'm not talking about the mean SST, those indirect things. I mean, directly the moistening is probably these 2 are the major parts.
I think I mean, they would be the 2 that I would highlight as being potentially most important. Yeah.
Yeah. So when we looked at the BSISO northward propagation, so if you for the MJO case, if you look at the moistening of the column, you will see in the boundary layer, if you go in any of the Sue and Lee or Adams and Wallace and look at the structure of the moistening, in the boundary layer, the moistening is due to the moisture, boundary layer moisture convergence, while in the free troposphere, they have shown that advection, horizontal advection roles plays a big role but in the region of moistening. But in case of BSISO, where the region of moistening, where the moisture tendency is positive, you will find the moisture convergence is basically negative. So, and the evaporation is also the evaporation anomaly, that's also negative. So these 2 way cannot directly help in the propagation. But still you have worked with Wei-Ching Han, and you have also found that if you do a calculation like Back-Bretherton, still you can find some positive contribution towards the moistening of it. So can I see it as like if you don't consider this gradient effect of the Lindsay-Nigam or Bagrathan style, then the negative effect due to the moisture divergence, not convergence, as I'm saying, in the where your tendency is the highest, you will get not a positive convergence but a negative convergence. But if you don't take this gradient effect, will it go more negative? That's in that way the moisture convergence is helping in case of northward propagation. Is it? Can I think in that way?
Well, I guess one thing I might disagree with a little bit is like Guang Wang showed that. I mean, it depends on what you mean by moisture convergence, I guess. Q del dot V or del QV. So there was actually a positive anomaly of del QV to the north of the MJO center being caused by zonal moisture advection.
Yeah.
That Xu Guang showed. So that's a little bit different maybe than.
Yeah, so advection is of course positive. If you write it as horizontal advection plus moisture convergence,
yeah.
Advection is positive, but moisture convergence is negative where you have the positive tendency.
Mm-hmm. But anyways, going back to the idea of so these moisture mode models are, one of the tenets of them are weak tropical temperature gradients. And that's a perfectly good assumption above the atmospheric boundary layer. But there's processes within the atmospheric boundary layer where temperature gradients are not small, and they're dictated more by the ocean Rossby radius than they are by the atmospheric Rossby radius. And these are processes that aren't directly applicable in a strictly weak temperature gradient process model that I'm hand waving, I don't know, that Adam Sobel and I had to indirectly include, for example, in our moisture mode model in other ways.
So I think it will be better if I show you the plots and
maybe show me the plots because
Yeah.
Can you pass the microphone to be here and then.
In the morning, we have learned that those models which actually simulate background moisture well actually do good in simulating MJO or BSISO, at least in the climate models. I just want to ask, does representing this ocean atmospheric coupling probably help in capturing the background moisture, correct?
Yes, I think so. And specifically that paper that Charlotte Demotte wrote in 2016, I think showed that. Is that, in that paper, moisture gradients and convection, gradients and convection, we're more concentrated, towards the equator. So I think it's consistent. At least some of these models, it's consistent with that sort of argument. Yeah.
Adrian.
I just wanted to come back to the issue of the sensitivity to the mixed layer depth, and you were showing how when it got too thin, then you started to not have so much of an amplification. And so I presume the sweet spot in terms of the mixed layer depth depends on the propagation velocity of the wave in question. So the slower moving the phenomenon, and then the sweet spot would occur at a larger mixing layer depth, whereas a very fast moving phenomenon or wave would basically have a sweet spot at a much thinner, faster responding ocean depth. So turning that on its head, presumably for a given mixed layer depth, would you expect some kind of scale selection or propagation velocity selection according to the feedback? And could it be that some models that show a weaker response basically are because there's a mismatch between their effective mixed layer depths that their ocean models representing through the vertical resolution or so on, and their underlying wave velocity. So there was a kind of a hint of that when you reported the IISc, and you said that there was a change in the period when they switched on the feedback. So I was just wondering if there's a kind of a possible role of kind of scout selection, amplification of certain, should we say, wave speeds through this feedback for a given mixed layer depth.
I think that's perfectly possible, and actually it's consistent, like you just said, with my results. I mean, with a 2 meter mixed layer depth, you get something that propagates very quickly off to the east at like 15 meters per second or something like that. It's interesting. So motivation behind this study originally that Adam and I did was their work on, one-dimensional ocean models and getting natural timescales out of one-dimensional ocean models as an explanation for the MJO. But I think what you say makes sense. I'm not aware that anybody has thought about that before. It'd be really interesting to look at this across models and see, because I think there could be something there. Yeah. Yeah.
Hello, nice, great talk. So I just wanted to know about this. Once you showed this a decomposition of the thermodynamic versus dynamic component, right? One of the slides.
Yeah.
So possibly slide number 8, possibly.
Yeah.
I noted.
And I don't think I actually did show the dynamic component, but yeah.
Yeah, something like that.
Yeah.
So on before that also. So the question is that since MGO involves several time scales, as well as spatial scale, right? So within the MGO, there are westward propagating small disturbances, right?
Yeah.
And that in itself, because we have also learned that from your talk and the previous talk, that it also interacts with the mean condition, isn't it? So therefore, this V and Q possibly are related to each other. And when you are talking about different time scales, like a much shorter time scale versus even longer time scale, how is it really possible to decompose like that? Question number 1, or even go to even a little more higher, or the deeper question is that if you have to estimate the bars and the primes, how do you estimate those? What should be the time scale for these bars and primes?
Yeah, no, I think this is a really critical question. I mean, I haven't thought about that particular issue in the context of this, this flux problem, but we have thought about that issue in the context of the moist static energy budget as a whole and the effect of eddies on horizontal advection. So in one of my papers, we looked at the importance of this Q prime, V prime term. I guess that's horizontal, not vertical, but horizontal. And we actually showed that synoptic timescale disturbances, things between 3 and 10 days, make up about half of the meridional advection associated with moistening during MJO events. So and it is sensitive to your assumptions about how you separate scales. So it is a little bit tricky. So I think it does need to come with care. But I think at least for some problems associated with the MJO, that you cannot neglect this term.
Okay.
Yeah.
Okay.
Yeah.
Yeah, thanks for the interesting talk. My doubt is about the present MJO evolution in the Indian Ocean. Like we see that in the Indian Ocean and the Equatorial Pacific, the changes in SSTs over 3.4 seems to be quite quickly responding to the phases of MJO when we have westerly or easterly anomalies. So in that case, we might have fluxes changing the SST anomalies in that region compared to the slow-moving oceanic waves. So between these two physical processes, the slow-moving oceanic waves and the quickly responding fluxes in the ocean surface, how do you differentiate like which would dominate the background sea surface temperature anomalies?
That's a good question. Dave Raymond has thought a lot about the effect of fluxes in the East Pacific on MJO dynamics. He's probably thought more about the upper ocean heat budget and those regions and those competing effects. Yeah, I don't know. I mean, certainly, when you do have these slowly propagating, thermocline depth anomalies associated with, MJO Kelvin waves, they are very, very effective at warming the upper ocean, by basically shutting off the thermodynamic effect of upwelling in those regions. So at least that slow response dominates
Yeah, maybe at high frequencies,
Yeah,
it looks like the
but as
fluxes.
far as the higher frequency periods, within 20 to 30 days, there, I mean, I'm sure it's the fluxes that dominate.
Yeah, this year looks like that. Because
Yeah.
La Nina has not
Yeah.
transitioned and seems
Yeah.
the MJO is changing the SST anomalies through higher frequency fluxes.
Yeah.
So, yeah.
But then if you had a really strong Kelvin wave coming in the ocean that, comes at a later time and, overwhelms that response and creates a strong SST anomaly, then things might change. Yeah.
Thanks.
No question.
Nice talk, sir.
Thank you.
During IOD cases in the Indian Ocean, month of the May, the cloud convective heating after releasing of the heating, how it is impacting of the MZO propagations? Positive IOD case.
Let's see. So positive IOD, so you're asking how it impacts MJO propagation?
Yeah, like
Yeah.
normally we will consider the propagation towards northward propagation, MJO. Then what in the IOD condition, if it is favorable for the MJO propagation, or it is strengthening the MJO propagation, or the convective cloud heating is also plays a key role. When the surface also evaporation will cools, the cloud will weakens. That case, the MJO propagations, it will more intense or less intense for Indian monsoon case.
I don't know. I don't know the answer to that question. That's a really good question. Yeah, I mean, I know that there have been studies done on this in a climate change context, where if you get a climate warming pattern that looks like a more of a positive IOD versus a negative IOD, you generally get a weaker overall MJO in general.
Okay.
Takahashi, did some work on that. Versus this case would be a stronger overall MJO in general. But as far as like the direct impact on propagation, I don't know. Yeah.
Okay.
It's a good
Thank you.
question. Yeah.
Any more questions for Eric? Right, if not, we'll break for lunch now and resume
Thank
at 2. Let's thank Eric one more time.